far.
Huh?
Both far.
Okay. So this is 9 and so it has 6 and 9. So we'll pick this, but all its neighbors are already optimized, so I don't need to do anything. And now, so since that is optimized, so this is the only one left, and both its neighbors are optimized also. So everything is done. Okay? So you again can put together all those dark edges, and this is your shortest path 3. Okay? So now we are going to do some theorem proving. So we saw the algorithm and its working example. So before that, let's try to look at the pseudo code of this. An exam I give you the pseudo code and ask you to analyze the runtime complexity, how long it will take. So let's do that. Okay, so what we did there in the algorithm, we have to start with 0 as the weight of the source vertex, right? And to every other vertex, the path weight estimate was infinity. And that's the initialization I'm doing here. For every vertex, I'm going to set the estimate to infinity. And then for the source, I'm going to set the estimate to 0. And at the end of the class last time I said we're going to store all those vertex weights, the path estimates in a heap. So we're going to store all these things in a heap. Okay? So if you want to, in each iteration, we want to pick up the minimum of these numbers, right? So we have to store that in a heap, and the heap we are going to use here, what I say, is a min heap. So what is the property of a min heap? How does it look like? So the root will be one of the smallest values. And then its two children have to be greater than or equal to the root. So the previous chapter we saw max heap. In the max heap, the root is the largest one, and it has to be greater than or equal to its two children. In this case, the min heap, the root is the smallest one, and it has to be less than or equal to its two children. And same thing for all the intermediate nodes. So, and we know from the heap chapter how long it takes to construct a heap. Let's say we use what? The bottom-up strategy.
Bottom up is just theta.
Theta of V or N. Here we say V, the number of vertices. Okay? And then if you want to remove a root and then rearrange a heap, how long it takes for one removal and rearranging?
Is it title log V?
Log N. Yeah, so log N, which is log V. Good. So this is for each removal. Okay, so each time you remove a vertex or even add a vertex to the heap, you have to rearrange the heap. So that takes theta of log V time to rearrange the heap. Okay? So you have to know this time complexities. So to start with, we have to construct the heap of all its values. Of course, 0 and everything else will be infinity. When you implement it, of course, you cannot use infinity, right? You have to use a very large number, which you won't get as a pathway. Alright, so we have here the two sets of vertices. One set, which I call by the set S, the set of vertices for which you have found the shortest path from the source. Okay? And the other set for which you know only an estimate, which I call it as Q. To start with, you don't have anything in this set S because you have not found the shortest path to anything, including the source. So the Q has basically all the vertices. Okay? And then we are going to remove, and this is the Q that is implemented as a priority Q. So to rhyme the same thing, I call this as Q itself. So it's a priority Q, and we saw that priority Q can be implemented as a key. So a standard regular Q is first in, first out. As a priority Q is kind of what? The keys will be stored in the increasing or decreasing order. So in this case, it is in the increasing order. So the one in the root or in the front of the queue will be always the one with the smallest value, so that you can dequeue it we said in the examples, when we say we pick the minimum value, we have optimized that vertex, right? Which means you have found the shortest path to that vertex. So then we will try to relax its neighbors, try to see if we can reduce the weight to its neighbors. That's what we did. So we'll do that here in each iteration. We'll remove the mean, extract min will give you the root of the heap. So that's the vertex u. Remember that notation I said. So you have the source S and your optimized is u. And then what you do, you go through its neighbors. So for every edge u to v, so you go through each of its neighbors. So let's say the neighbor is denoted as v. Okay, so you have the edge weight u comma v, and this is the estimate of the path. This is what you have optimized now, and this is still an estimate. So what we want to check, can we reduce this d of v by going through u? So we have to check if d of u plus the edge weight is going to be less than d of v. So again some numbers. So let's say this is 30 and this is 10 and this is 70. So far the estimate is 70. So now by going through u and this edge, can we reduce this from 70? And in this case, yes. So if that is the case, we will make this as the predecessor. Right? So that's what we are checking here. For every such neighbor v, we are going to check if d of v, the current estimate, is going to be greater than d of u, the weight of the shortest path to u, plus the weight of the edge. If that is the case, we can set the estimate to be now d of u plus the weight of the edge. And then we can make the predecessor of v to be u. So that's the portion where dark, like make the edge dark so that we can say that's the predecessor. So you do this only if you can reduce the estimate, otherwise you just leave it as it is. So now what happens? If this vertex v is in the heap, somewhere in the heap, right? So when its weight changes from say 70 to 40, what does it mean? You have to rearrange the heap because it's no longer, for example, if this was a 70, right? And this is a min heap, so this has to be less than its two children. So let's say its children are some 90 and say 100, and this has to be greater than the root. The root is say some 50. So now this has become 40, so which means this guy can no longer be the root. You have to move around things. You see what I mean? So which means you have to rearrange the heap, and that will take how long? Rate of log v time. You see what I mean? This was 70 before. This is a heap, valid heap. But if this changes to 40, you have to rearrange it, right? So that this becomes, or its parent is going to be less than this, and its children are going to be greater than this. So you have to maintain the property. So that takes rate of log v time. And how many times you have to do this? Overall, how many edges are there? E edges in that graph. So across all the iterations, you are going to explore those edges, right? In each iteration, you explore some edges. So if you put together all the iterations, you are exploring E such edges, the total number of edges in the graph, right? So in one iteration, you are exploring say 2 or 3 edges. Like the first iteration will explore these 2 edges. Then the next iteration, when you pick up this vertex, you are going to explore these 2 edges, and so on. So totally you are going to explore E edges, and each time you explore an edge, right, you may end up changing the weight of that end vertex. Like if you explore this, you are going to change this weight of C from infinity to 3, you have to rearrange the heap. Similarly, in this case, you are going to change the weight estimate from 5 to 4, you have to rearrange the heap and all every time, right? You may or may not, but in the worst case, you may have to do every time for every edge. So for each such edges, we have to rearrange the heap. That takes log v time. So that portion, that relaxation them is actually the most time-consuming step of this algorithm. So across all the iterations put together, you will have to do this e times, set of e times. So each time we do it, it takes set of log v times. So this step, don't see it as a loop, don't see it as a while loop, but just putting together all the iterations, it takes set of e times log v. Now this step, where we remove the minimum, the smallest vertex to root, right? When you remove the root, you have to rearrange the key. Remember, so when you remove the root, you have to bring something from the bottom and put that as a temporary root and then rearrange. That's how you rearrange the key, right? And that takes another set of log v time. And how many times you have to do that? That depends on how many times this while loop runs. So you want to make sure you start with v vertices and you run this loop until this queue becomes empty, which means you have to do v iterations. Like in every iteration you move a vertex and say you optimize that vertex. So we have total of v iterations that we'll do, right? Each time we remove a vertex, there's an iteration, and you say you have found the shortest path to that vertex. So each time we remove the vertex, you're adding to this set. What does it mean? You have found the shortest path to that vertex u. So this set S grows. Remember I said to start with that set is empty. Each time you say you have found the shortest path to a vertex u, you're going to add that to the set S and then remove that from this queue. So you run this loop until this queue becomes empty. So we have total of v iterations for this loop, and that will be v log v. So each time you do remove the root, you have to rearrange the root, the heap. So it takes v log v time for to rearrange the key because of the root removal process. It takes e log v time to rearrange the key because of the relaxation step. Okay, so this is because of the relaxation. This is because of the root removal or optimization. You say you optimize the vertex, the path to a vertex, right? So each iteration you optimize the path to a particular vertex that you have found the shortest path to some u. So the total time complexity will be this plus this, right? Understand this part? Each time you want to run, what you do, each step you say I have found the shortest path to some vertex, right? So this step you remove this a, so that's the root of the heap because that's the minimum of all these numbers. And then the next step you remove this vertex. So when you remove this from the heap, you have to rearrange the rest of the values, make another vertex of the root, which will be this 4, right? And then you remove this, you have to rearrange the rest. So each time you remove a vertex, you have to rearrange the heap. That's this part, v log v. And this one comes because of traversing the edges to reduce the weight. So the total complexity will be e log v plus e log v log v. So you can just say this is data of e plus v log v. Okay, so that's the time complexity of this Dijkstra algorithm. Okay, clear? Now, just as a side notice information, additional information you may want to know. In a graph, the number of vertices or the number of edges, if you want a connected graph, the minimum number of edges you need is v minus 1. If you have v vertices, say 10 vertices in a graph, to connect all these 10 vertices, you need at least 9 edges. Or even like if you say 4 vertices. If I want to connect these 4 vertices, I need at least 3 edges. If I just have 2 edges, I cannot connect all the 4 together, right? So if I want them to be connected, which means reachable from each other, I need at least 3 edges. So if in general you have v vertices, you need to have at least v minus 1 edges. And at the worst case, you could kind of connect them directly to each other. Okay? So that would be how many edges? We did that before, you remember? 1 plus b minus 2 plus so on up to 3 plus 2 plus 1. So what is that? We saw this in the first part of the course. Summation 1, 2, or 3 up to b minus 1. That's going to be I have to make the finals to have all these things. You're not going to tell. So this is going to be, if you have 1 plus 2 plus up to n, it's going to be
N.
n.
No, I.
N times n plus 1 over 2. This is theta of n squared. Okay? So if we have 1 plus 2 up to n minus 1, you replace n with n minus 1. So that's going to be what? N minus 1 times n minus 1 plus 1 over 2, right? That's going to be n times n minus 1 over 2. So n times n plus 1 over 2, that is n times n minus 1 over 2. So it is still theta of n squared. So we can say E is at least theta of B, and at the worst case it will be theta of B squared. Okay, so the number of edges, this is the minimum bar, and then
And that's the maximum?
yeah, so this is in the case of a tree. A tree means what? You don't have any cycles. So if you have 4 vertices, you connect them like this. Right? So that's a tree. Whereas this is the case of a mesh. Mesh means you're fully connected. Each vertex can directly reach the other vertex. In the case of a mesh, it is theta of b squared. Okay? So, which means if you assume that the graph has, at the worst case it could be a mesh, right? That could be the maximum number of edges, isn't it? Right? So if you are given a network of cities, and let's say every city is directly reachable to every other city, then it's a fully connected graph like this. So, which means I can say this E is going to be B squared. Right? So, you see what I mean? I can say this is B squared basically. Right? So I'm having B square log B and V log V. Is that clear? That number of edges would be at most V square. Right? A fully connected graph. So I can say this is then instead of V square log V and then a V log V. So if we have something like this, what's the complexity? V square log V plus V log V is? You want to come here, you cannot see. You go sit here. Sit here.
I can see.
You can see. So what is this? V square log V plus V log V is? Log V is there in both of them. And you have V square here and then V here. So which is more dominating? That's the first thing we did in the course. You want me to put this notation? So you have theta of V square log V plus theta of V log V. So which is more dominating of the two? V square. So that is V square log V. So if you want to just write in terms of V, we can say the complexity of the
us to memorize the bold text on this slide? And
Don't memorize
or
it,
learn
try
it.
to-
Learn it, I'll say.
Right.
Learn it.
Trying to understand the bold text means the time complexity. Okay, I'll give the pseudocode, but you have to analyze the time complexity for each step. Alright? Okay, so let's try to prove now the correctness. So as I said, we'll have some proofs. The first proofs are easier. So the subpath of a shortest path is the shortest path. You understand what does it mean? It's a theorem. The subpath of a shortest path is the shortest path. What does it mean? You have, say, a source to some vertex B or destination, let's say D, and you have some intermediate vertices. Let's say you have this is U, this is V, and let's say W, something. Okay? Let's say I have the shortest path from S to D. Shortest means in our context the minimum weight path. So let's give some numbers. So let's say this is 4, 5, so it adds up to 19, right? So the minimum weight path from S to D, or the shortest path, that's what we mean by shortest path, is the weight is 19 from S to D. So the subpath, let's pick a subpath here, which is this, U to V. What's the weight of the subpath on this thing? Is 5 plus 3, which is 8. Right? So the theorem states the subpath of a shortest path is also the shortest path, which means from U to V, this is the best path we can have of weight 8. U to V, that's the shortest path. That's the minimum weight path. Right? Is that clear? How is that? Can you prove this? How can you prove? What is the given that S to B is the shortest path? Alright? Given that you have a shortest path, S to B, we want to prove what? Some subpath like U to V is the shortest path. So path always in our notation will denote with the wavy edge like this, so wavy thing to denote this is the path. So we want to prove that U to V is the shortest path. How would you prove this? What technique you have seen so far? Last class, what technique you use for proofs? Huh? Prove by contradiction. Can you prove by contradiction here? So how do you do by contradiction? Let's say there is some, this is not the shortest path, there is something else which is the shortest path. Okay? So you want to argue whether that such a path can exist or not. Right? So let's say there is some other path from U to V of weight less than, what is the weight here? Let's say, we can just say weight, let's say this is the shortest path P. Okay? So there's some other path P prime from U to V, and the weight of P prime is going to be less than the weight of P. P is this path, and let's say there's some P prime that is of weight less than the weight of P. The question is, can such a path exist? If such a path can exist, what can happen? That means you have some alternate path, right? This is an alternate path, isn't it? Instead of P, you have an alternate path from U to V. Some alternate path. P prime, right? This is your P, this is your alternate path P prime. If the weight of path P prime is going to be less than the weight of path P, what I can do? From S, I can go on this path P prime and I can reach this D. Right? So it means the weight of the path from S to D can be lowered further than 90. Isn't it? If this path is going to be of weight something like less than 8, right? So let's say it is going to be 7. I can go from S to this, which is 4, and then take this path. The total weight of this path is 7. So 4 plus 7, 11, plus 7 is going to be 18. So I can further reduce the weight of the path from S to D, from 19 to something lower than 19. Right? But what is our assumption? S to D, the big one, is the shortest path. So which means it contradicts our original statement that S to D of weight 19 is the shortest path. It's no longer the shortest path. If such a path P prime can exist, S to D, whatever we have, is no longer the shortest path. Right? So that's a contradiction. You see what I mean? So which means such a path P prime cannot exist. If that exists, the bigger one, the S to D, is not by itself a shortest path. Okay? Is that clear? So that's why every subpath of a shortest path is also a shortest path. Okay? So that's how we have to prove this. That's what I've given here as the statement. Instead of U, V, I'd say A, B, C, so it's the same idea. Right? Okay, so that's the first theorem. The second theorem is, so your upcoming quizzes and exam may not be take home because you have whose theorem I want you to come here and take them. Okay? So better focus on the class. So, what you want to prove here is, remember in each iteration, we pick a vertex and say, we optimize that vertex, right? And say, that means what? We have found the shortest path to that vertex, isn't it? So, which means I have found the shortest path. If I pick a vertex, say U, right, of some weight, in each iteration, I say I have optimized that vertex, right? That each step you say you pick the minimum weight among these vertices and you say all this, each time you pick a vertex, you say you optimize